Hey everybody, and welcome back to Algebra 2 online. So this video is going to just show us one of just many applications of logs and exponentials, and probably one of the most prevalent and the ones that most of you may end up seeing. If you end up going into business really in any sort of way, you're going to start to see a lot of applications in finance. I have friends that have gone on to get like MBAs and things like that, and they use this stuff all the time. But what I really want to show today is basically three different formulas really that relate, that involve like they're exponential models for growth in finance, and you can like solve problems with them. And if you're going to solve exponentials, you're going to probably need logs. So that's kind of what you'll see today. So the first one I want to show you is right here. This A equals P times 1 plus R to the T. And some of these letters might kind of just be intuitive. I bet a lot of you would think correctly that this is rate and T is time. P and A are not probably as clear. So you can think of A as sort of just the end amount. Really the fancy word is accrued amount. That is spelled, I think, A-C-C-U-R-E-D. But the accrued like interest is basically what you get after a certain amount of time at a certain rate in an account, basically. It's just your end amount. And P is really your basically just your starting amount. But fancy word there is basically the principal amount. It's really just what you started with, okay? And all these, I did the wrong spelling of principal there. It's this one. I think I dropped an I. I don't know how to spell. But basically this picture kind of can sum it up. So what we're talking about here is these ideas where you stick in some sort of base amount, right? So here, it's cut off a little bit, but basically you got like $1,000 in this account. And over time, which is this axis, right? If your interest is compounding, that will grow exponentially, because what it's doing for compounding interest is it basically adds the interest you've gained back in and then calculates based off that rate the new amount in the account, right? So it's going to be a higher number, and as you get more and more and more money in there, it grows faster and faster and faster. If the interest is not compounding, you would just have like a linear growth, based just a constant growth like that, based on the rate and things like that. But this is why you can get these like crazy models, and it says like, if you start investing in your retirement at the age of like 25 versus 30, like the difference of just what 5 years can make, it can be really significant. Those are important things to kind of look into when you get a little older. I want to start off and just kind of show you where this equation comes from. And so the way you want to think about it is so let's take it in terms of years. So in the first year, right, you have the principal, and then you just apply 1 plus R, because you want to think of this as like, you want to multiply it by, the rate is going to be like a decimal, like 0.001, probably like quite a small number in reality. And if you just multiplied P by that, you're going to get less money. But we don't want that, right? So you have to do 1 plus that growth rate, basically. And so if we do that out, right, we're going to get, if we just distribute it, we get P plus RP, right? And that's like the total, this is my A, my accrued interest after 1 year. Then on the second year, right, now what you're basically doing is you're taking the amount in there, which is P plus RP, right? And you multiply it by 1 plus R. But if you think about it this way, you can factor out a p from, here and here. So you take that p out, and then you got 1 plus r times 1 plus r, or just p times 1 plus r squared, right? And so you can start to see where the formula comes from, because what you basically just keep doing, right, is like in the nth year, you're just going to have like p times 1 plus r times 1 plus r times 1 plus r, right? All n times, which you can just write as p times 1 plus r to the n, right? But basically you want to think about the little parenthesis part as just what you like tack on every single year to the principal, and then you're going to get more and more and more money. That's the idea. So this is only for problems where it's compounded yearly. So the big difference in the formulas you're going to see today are how they compound it. Some accounts really do compound yearly, and it turns out that actually a lot don't in reality, and they use some other techniques that I'll talk about here in a second. But for right now, we're just sort of supposing that they really do just compound yearly, okay? So in this problem, we have an initial deposit of, $1,000, and the account pays 3% compounded yearly, which honestly is an insane amount of interest. A lot of times it's fractional percents, but whatever. The question is, how long will it take to get $1 billion? So you just let the money sit there, and you never touch it. How long is it going to take to get $1 billion? So you're going to use that a equals p times 1 plus r to the t. The end amount you want is 1 billion, right? So 1 billion has 9 zeros like that. And the principal is 1,000, right? And then you need the 1, so you basically don't lose money. And then your rate, you never put it in as a percent like that, right? You always put it in as a decimal, so it's 0.03. And then the question is about time, right? So we're going to solve for t. I would simplify by dividing, by this 1,000 right here first. So if I do that, I'll get, 1 million now equals 1.03 to the t. And then, we should know at this point how to cancel off that exponential. You just take log base 1.03 of 1 million. And honestly, that's the answer. But if you plug that into a calculator, you get something that's like a little bit over 467 years. We'll just round it to years. Quite a while, right? So probably not a good way to try to become a billionaire. You probably need to invest a little more money than that. And again, remember that this is an insane interest rate. You're never going to get that, really. So honestly, it would probably be a lot longer than that. But there you go. That might be depressing, but that's the truth. All right, so the next kind of finance formula I want to talk about is where we compound the interest n times per year for a period of like t years, okay? So we're still going to apply the same total rate over the course of the year, but instead of only applying it at the end of the year, let's say, we do it throughout the year. So like a lot of accounts, you might do it like a quarterly application of the interest. So you still have the full rate over the year, but you apply it, 4 times as much. So inside here, you're not going to want to put just R. Every time that interest gets applied, it's like R over 4, because eventually you'll have 4 of those to equal out to the full amount. And then if it was like a monthly thing, right, you're going to have this rate split up into 12 even chunks per month, and you apply that each month, and then, so on and so on. So basically the way you can think about it is if you do it quarterly, right, you would have like the principal times, let's just say it's quarterly for 2 years, right? you're going to have 1 plus r over 4, and then you have, it's quarterly, so you're going to have 4 of those in 1 year, right? So you can kind of think of this as 1 year's worth, right? But then you have that thing for another year, right? Again, that's like your second year. And so what you basically get is you get 8 of these, right? And which, in this case is 4 times as many as the total years, right? Because there's 4 times in a year, so you just literally would multiply, right, to figure out how many applications of this interest you do. If you think about generalizing this, right, basically you're just going to take your accrued amount is always just going to be your principal times 1 plus whatever the rate divided by the n times per year you have is, and then you'll just have to scale, how many times you're doing it per year, basically, right? Like if you do the 12 months, you'll have 12 times per 1 year. So if you did a 2-year chunk, you'll have 12 times 2, which is 24 times, right? Which is 24 months in 2 years. And this is just here because we're taking that rate, and that normally that rate would be spread out over a year, but we split it up into n chunks, right? So this right here is basically what we use for problems where the interest is compounded n times per year. That's your formula for that, which really is just similar to the last one, but it's just kind of adding a little bit to it, and these will always match. So there's one more, and then I'm going to do a problem where we kind of link it all together, okay? So if you think of this kind of problem, right, but you think of the concept of taking n to be literally not just 4, not just 12, not like 365, like 1 per day. Like imagine you let this n subintervals just be like infinite. So basically if it was infinite, it would be analogous to a continuous compounded interest. And in continuous compound interest problems, you get what looks like a brand new formula. You get this thing that's a equals p e to the RT. And to see where this comes out of, we've actually sort of seen it, okay? But we need something called a limit, right? And if we really understand how to use a limit, we can see why when n goes to infinity, so this is like just constant, continuous implying of the interest, that interior part, the 1 plus r over n, that's actually going to go to e. This is kind of a breakdown of it. So if you do a yearly thing, right, you'll have 1 plus, this is where the rate is like 1, basically, just for simplicity's sake. But you have 1 over 1, all of that, right? This is just 2, right? And then if you keep doing this, if you literally just multiply all these things out, the ends are getting bigger and 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 bigger. And you'll see that these numbers get closer and closer and closer to that number e, that 2.71828, blah, 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 number that we've seen. And truly enough, if you take n to infinity, then this thing in here will go to e, okay? And so whenever you see this right here, compounded continuously, that's your clue that you'll need to use this one, okay? So let's suppose that we have 10,000 to invest, and we want to have at least 25,000 in an account in 10 years for a new car. If the account pays interest compounded continuously, what rate would basically be required to do that, Okay, so if we just use this thing and set it up, we want 25,000 at the end. We have 10,000 to invest, which is a pretty good amount, right? Compounded continuously, so we got an E there. And we want to know the rate, and we want this money in 10 years. So we're going to put a 10 right there, okay? So divide out by the 10,000, and we would get 2.5. And I really actually could be even more careful here. So we said we want to have at least 25,000, right? So this amount over here, this can surpass 25,000, right? So really the best thing to put here is an inequality. We want to have at least 25,000, so we should allow for it to be bigger than it as well. All right, so basically now to solve that, right, we just use natural log. We take natural log of both sides. That'll cancel the E. So then you have natural log 2.5 less than or equal to 10R. And then if you divide by 10, basically R is got to be greater than or equal to 2.5 over 10. Natural log of 2.5 over 10. And this thing is about 0.09, so that's like about 9%, which is an absolutely insane interest rate that you would never, ever get. So basically, if this is like the setup that you have in life and you really want this much money, which nowadays doesn't even really buy you much of a car, then you really are going to need to go some other route, because you need to take loans or something like that, because you're not going to be able to afford it that way. But that would be the interest rate if the interest was compounded continuously. All right. So the last thing I want to do is kind of just put all this together. So let's say I won $150,000 in the Colorado lottery, and I'm trying to decide how best to invest my winnings for retirement in 20 years. There's three options. So a certificate of deposit paying 4.5% interest compounded yearly. Again, crazy interest rate. A money market certificate paying 4.3% interest compounded semi-annually, which is just like 2 times a year. Or a bond paying 4.4 interest compounded continuously. So I think a lot of times in these problems, people think the compounded continuously should just get you the most money, right? Because if you just constantly, like, if I go back to this picture, if I'm just constantly dumping money back into the account, then I recalculate the interest on that amount and apply it, right? If I just keep doing that loop, it seems like it should grow that way would grow it the most quickly. But there are other factors, and one of the big ones is the rates. So another option I think people might think is, well, maybe I'll just go with the biggest interest rate. This one being 0.1% higher than that one. Maybe that's the best. But that one's only compounded yearly, so it's kind of the total opposite of this one in terms of how often it's applied. So maybe it's actually not a good option, right? So you need math to do this kind of stuff. And if you just plug in, out of these three formulas that we just saw, you can solve and see which one gives you the most money, okay? So for all of them, I'm solving for A. And in this first one, the initial amount is always the same too. I have 150,000, 1 plus 0.045, and then I have 20 years, right? And if you solve all that out, okay, A is about 361,757.10. So 361,000 and some other change. In the next one, again, 150,000. And then 1 plus, so semi-annually is just 2 times per year. So we take my interest rate of 0.043, split it up into 2 even chunks, split out over the year. But now, now I have 40 applications of that interest because it's twice for each year. So it's 40 times total in the 20 years. So then if I do that one out, you're going to get about 351,257.90. And then the last one, 150,000 again, E, and then I've got 0.044, and I've got 20 years of that, continuous compounded interest. And in this one, A works out to be about 361634, 0.96. So all actually fairly close, okay? But if you really want to max min everything here, turns out that this is the biggest one. So the best option would basically actually be that first option. And a lot of times what you'll notice is if the interest rates are different, it's pretty hard to beat the highest interest rate. So don't always just take the biggest interest rate, because a company or a bank or something can be trying to sell you based on that idea where they're just like, here's the biggest interest rate. They're trying to pull you in. You should just go and do the computations and figure it out. But it is a lot of times the case where whatever one gives you the biggest interest rate will actually be the best option. It's just hard to beat that growth rate being bigger. That's the idea. So this is just one application. If you go into business school, major in business in college, those kind of things, you're going to see all this all over. If you go obviously into like accounting, a lot of law uses stuff like this, depending on the kind of law that you study. Very, very prevalent. And all these models can be applied to other applications in science, and that's kind of what we'll see in the next application video. There's going to be a very similar looking formula to this one that we'll be working with. But I wanted to take some time and do some problems just associated with these finance ones first.